last video, we looked at calculating percent composition. In this one, we're going to go kind of backwards. We'll be given the percent composition of a compound, and we want to determine its formula. These few examples in this video are going to be using an empirical formula. Empirical. Formula. The empirical formula, you might recall, these are going to be ionics. Ionic compounds are always written with the simplest ratio of ions. That's called the empirical formula. And now we could have covalents that also have an empirical formula, but sometimes covalents have a larger ratio, which we'll deal with in the next video. So specifically now, we're just looking at empirical formulas, which are going to be the lowest or the simplest ratio of atoms or ions. Usually empirical formulas are looked at in relation to ionic compounds, which is what we've got in this first example. If you see a metal listed, you know it's going to be ionic. This compound has calcium, oxygen, and hydrogen. We want to know its formula given percent composition data. So the first thing we do is assume a 100-gram sample. If I had 100 grams of this compound, and it's about 54% calcium, that's like saying I would have 54.09 grams of calcium. And the sample should have 43.18 grams of oxygen and 2.73 grams of hydrogen. By assuming a 100-gram sample. Now, technically, you could assume anything. You could assume a 200-gram sample, a 500-gram sample. But then you would have to multiply that sample size times your percent to switch it into a mass, which is what I want to work with in a second here. So a 100-gram sample is usually easiest because then I can just take those percentages and use them as grams. I know the elements. I know this is going to be like calcium something, and then it's going to have some oxygen, and it's going to have some hydrogen. We just don't know that XYZ ratio. What's the ratio of elements in this compound? Now, when I look at a ratio in a formula, it's a ratio of atoms, number of atoms, how many calcium atoms, how many oxygen, how many hydrogen atoms. So I want a unit that measures numbers of atoms. Okay, well, grams was easy from percentages. I could easily take those percentages, assume a 100-gram sample, put them in grams, but grams does not directly correlate to number of atoms. So obviously I can't say that there's like 54 atoms of calcium or something crazy like that. Our unit here that we're looking for, you guessed it, moles. We want this in moles because moles would be a unit that represents and lets me compare amounts of particles. So by taking those percentages and using them as grams, I can easily switch them into moles, which is a unit that I can work with. So for all of these, we're just going to cancel grams, put them into moles. The periodic table will tell me the mass of 1 mole. I just got to look it up. 40.08 for calcium. Cancel grams. I want moles. 1 mole of oxygen. My periodic table says 16 on the dot. And then hydrogen. Cancel grams. Put it into moles. 1 mole on most periodic tables is approximately like 1.01 grams. Some periodic tables will say like 1.008. So use whatever's on your periodic table, at least 2 decimal spots. All right, so we're going to plug these in and we're going to calculate moles. And again, sig figs here aren't essential. My final answer is a formula. So when you plug this in your calculator and solve for moles, again, I'm not going to punch you in the face if you don't have the right number of sig figs at this point. However, using the amount of sig figs in the given data is a good guide. So when I plug this in, I'm going to just leave 4. 1.3, I'm going to say 50 moles of calcium. I'm going to leave 4. And this next one, oxygen, 2.699 moles of oxygen. And now the hydrogen, technically I'm starting with 3 sig figs, but I think I'm just going to use 4. We'll keep it consistent. 708 moles of hydrogen. These are not my final answers. So if you left 2 decimal spots, I could live with it. I would be fine. In the end, we're looking for a ratio, and we're going to apply that ratio to our final formula. The more precision you show in these mole calculations, the easier it might be to calculate a whole number ratio. So I look at my data. These are not whole numbers, 1.3, 2.7. However, I can make them whole numbers. If you do get to this point and you would have had like 1.99 or 2.01 or something like that, you're probably close enough to whole numbers that you can apply that to the formula right away. These are not whole numbers. However, you might be smart enough to see the whole number ratio at this point. I've got a ratio of about 1.35 to about 2.7. I'm going to guess this ratio is going to turn out to be about 1 to 2 to 2. If you can't see that, the first trick to try, divide them all by the smallest. Originally, these were not whole number ratios of moles. Hopefully, I can divide by the smallest, and they will be whole numbers. I know at least one of them is going to be a whole number. I'm dividing him by himself. Then we'll go through and divide everybody else by the smallest. And now, within reason, I should be looking at whole number ratios. This is approximately 2 and approximately 2. For whole numbers, again, if the decimal turns out to be like 2.01 or 1.98, that's close enough to round. So here we've got our ratio, our whole number ratio, 1 to 2 to 2. So now people apply that to the formula right away. They'll get really excited and they'll say calcium, there's going to be 1. Obviously, we don't have to write 1s in the formula. Oxygen, there are 2. Hydrogen, there are 2. They'll leave that as their final answer and they lose a half a point. And they're really sad, disappointed. What did I do wrong? If you notice there is a metal in the compound, the compound is ionic. Ionic compounds will have 2 ions, the positive cation and the negative anion. The metal will always be the positive, unless we're dealing with ammonium ions. If you notice 2 non-metals, I will bet you $100 it's a polyatomic ion. So look out for that. If I see OH, a little bell should go off and I should be like, ding, 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 that's hydroxide. The better way of writing this formula would be CaOH in parentheses, 2 on the outside. This is calcium hydroxide. Now, you might be smart enough, too, to be like, oh, duh. Calcium's charge is +2, hydroxide is -1. This is the formula of calcium hydroxide. If this would have been like sulfur and oxygen, I would bet money that it's going to end up being SO4 sulfate. Or if it would be like carbon and oxygen, I bet it's going to be CO3 carbonate. Keep your eye out for polyatomic ions, especially if the first ion is a metal and then the other ones are non-metals. I bet those non-metals form a polyatomic. So kind of keep your eye out for those ratios in common polyatomic ions. It is better to write this as calcium hydroxide. Another option, I like this one a little better actually. I've got a 12.5 gram sample of iron oxide. We must have decomposed it or something like that. So we know there are 8.75 grams of iron. The rest of the sample must have been oxygen. We want the empirical formula. What's the formula of the compound? The empirical formula being the simplest ratio. So we can get the individual masses of each element. And it's coming right out and telling me that there are 8.75 grams of iron. The rest of that 12.5 gram sample is the oxygen. 3.75 grams of oxygen. I like this one better because iron is a transition metal. So you can't just tell me, hey, it's an iron oxide, and I could write the formula. Now, if this would have been like calcium and oxygen, well, duh, I don't even have to do any work. I can write the formula of calcium oxide off the periodic table. But I don't know the charge on iron, so I have to do the work for this one. Okay, so we got the individual masses. We need to turn them into moles. Cancel grams, put it into moles. Notice that the data here was not given as percent composition. It was given right away as grams. That's fine, because if I had percent composition data, the first thing I did was change it into grams anyway. So I want these out of grams and into moles. 55.85 is the molar mass of iron, 1 mole. The original measurement was 3 sig figs. Let's try 3 moles of iron. I'm not going to take off points for sig figs at this point. That's really not your final answer. But I would leave a few decimal spots, maybe 2 or 3 decimal places, so that we leave enough precision that we get whole numbers in the end. We'll do the same thing with the oxygen. Cancel grams. We want it in moles. 1 mole of oxygen is 16 grams. We'll leave 3 sig figs on this guy too. 0.234 moles of oxygen. All right, cute. Now the last one, when I got to this point, I could eye up the moles and come up with a whole number ratio. I mean, I had an idea that it was going to be a 1 to 2 to 2 ratio. These are kind of goofy numbers. And maybe you can't come up with a whole number ratio off the top of your head. The first trick to try, divide them by the smallest. So we'll divide them by this 0.157, because I know that's going to give me a 1. Divided by 0.157, we cross our fingers. Darn it, not quite a whole number. I'm looking at about 1.49-ish. Okay, so the ratio is approximately 1 to 1.5. And I can't write 1.5 in my formula. I can't have 1.5 atoms of oxygen. So if you get to this point and they're still not whole numbers, it's probably something that you can manipulate into a whole number. If you get something that ends 0.5, multiply it by 2. If you would have 0.333 repeating, multiply her by 3. If it was 0.25, you could multiply by 4. And if you do it to 1, you got to do it to both. We have to keep this ratio consistent. It's a ratio of 1 to 1.5, which would be equivalent to a ratio of 2 to 3. There we go. This compound, Fe2O3, it's rust. From here, I might be asked to write the name. I might be asked, like, what is the charge on the iron? They could ask me other questions about this compound, but I'd have to start by getting the empirical formula. So there's a good example of one that I can't just write the formula by looking at the periodic table. I calculated moles, divided by the smallest, and still didn't get a whole number ratio, but I could make it a whole number ratio. The last one in this section is kind of where we're going in the lab. In the lab, we're going to get data that looks exactly like this. We're going to take a hydrate. This is a calcium chloride hydrate. We'll take the mass of the original hydrated compound, We'll heat it gently and dehydrate the hydrate, so that in the end, all we'll have left is the anhydrous salt, or the anhydrate. We'll take that mass and we'll use this data to figure out the original formula of the hydrate. If I wanted to think of this as kind of a equation, we got calcium chloride. Calcium and chlorine. Plus 2 minus 1. It's a hydrate, but we don't know how much water's in the compound. So we'll say question mark. That's exactly how the beakers are labeled in the lab. By gently heating the hydrate with, let's say, heat, gentle heat, we hope to just drive off the water. So we'll be left with calcium chloride. This is the anhydrous salt, or the anhydrate, as they're referring to it here. And then we're going to have some water. We don't know how much, but we should be able to evaporate the water. We can fill in a couple things here. We know the mass of the original compound. We had 4.72 grams. After heating, the anhydrate was 3.56 grams. So the rest of that mass was lost as water vapor. So if I subtract the two, I can figure out the mass of water vapor. 1.16 grams. All right, so now we're going to look for the empirical formula. What I'm really looking for is this ratio. For every one calcium chloride molecule, or unit, I could say, how many water molecules are there? So it's a little bit different than the empirical formulas, where I was looking for a ratio between like atoms and elements within a compound. Now I'm looking for actually a ratio of two compounds, but I can do it the same way. We're looking for a ratio of particles. For every 1 unit of calcium chloride, how many water molecules? What's that whole number ratio? And we do have some masses that we can work with. We have 3.56 grams of calcium chloride. And we released 1.16 grams of water. We're looking for a ratio of particles. A unit that measures particles is the mole. So let's just get these out of grams and into moles. It's okay that they're compounds. We'll add it up on a calculator. We got a calcium plus 2 chlorines. I get 110.98. And then we'll do the same with the water. Cancel grams, put it into moles. 1 mole of water, about 18 point, let's say 0.02. All right, let's get these out of grams into moles. We'll leave a couple sig figs. Let's see here. We'll plug this in. Oh, I don't know, about like 0.03208. I guess we could say 1. Let's try it. There's the calcium chloride. And let's see what we get with the water. 0.06. 4. 4 moles of water. And again, I wouldn't take off points for sig figs when you calculate the moles, but I would leave at least like 3 sig figs if the original masses were given in 3. I'm looking for a whole number ratio, and I want to leave enough precision to get that whole number ratio. Can you see it? These are obviously not whole numbers, but I have a guess. If it's not obvious to you, divide them by the smallest. 0.0321, because I bet that's a 1. And if I divide this by the smallest, I get darn close to 2. There's my ratio, 1 to 2. And then when I write the formula, I write this as 1 calcium chloride 1 mole of calcium chloride. I don't have to write the 1 in front. Then comes the big dot, 2 waters. For every 1 unit of calcium chloride, there would be 2 water molecules. If you put a little star by this one, it's exactly what you're going to do in the lab. You'll have the same type of data. You'll be doing the same kinds of calculations.